Hey everyone, today I'm going to be showing you what color a black hole is. I'm holding in my hand one of the blackest materials on Earth called Horizon Black Max. Okay, let's open this up and see how dark this actually is. Holy cow. That is black. This is significantly darker than any of the super black paints that I've showed on my channel before. It's made by building up little tiny hairs on an aluminum substrate that trap the light as it comes into it, and then it re-emits it as heat. But my question to you is, what color is this? You would say it's black, but that's only because it's a really small amount of photons coming off of it. But what color is it actually? For example, you can see that I have a black square here, but this isn't actually a black square, it's actually rainbow colored. But it's just letting off such a low amount of light that you can't see it. For example, let me shine a little bit more light on this. Now you can start to see it a little bit better. So the point is, no matter what color something is, including white, it always looks black if there's not enough light coming off of it. And the reason for this is because of the cells in our eye that are responsible for sight. For example, we have two different types of cells in our eye that respond to light. One of them is rods and the other one is cones. Now, cone cells can respond to different wavelengths of light differently. For example, we have ones that respond to longer wavelengths, ones to medium wavelengths, and ones to shorter wavelengths. And depending on how those combine together, we see different colors of light. But the rods are different. They just respond and tell us whether or not light is present at all. If you've ever been out in moonlight where there's really low levels of light, you'll notice that you can't really see color anymore. It's just kind of different shades of brightness. And that's because you're only using your rod cells. Now, what's amazing about rod cells is that they don't take a lot of light to be triggered. In fact, scientists have found that you can see as little as 1 photon at a time. So when you see a black object in your house, how can you tell what color it actually is? To me, this just looks black, but it could be a really dark purple or a really dark red or a really dark yellow. It's just not letting off a lot of yellow light, so it appears black to me. Well, the way to do it is just take a really bright white flashlight and shine it on it and see what color it looks after that. If it's still black, then it's probably that it's absorbing all the different wavelengths of light, and so it truly is black. And what do I mean by truly black? It means that it's actually just a different shade of white. White absorbs and reflects all the different colors of the rainbow. And so black and white are actually the same thing, they're just different brightnesses. For example, I have here some black construction paper, and it looks black, but that's only because there's not a lot of light shining on it. If you shine enough light on it, it'll just turn white. If I shine a bright flashlight on it at 32,000 lumen, it now turns into a white paper. Now that brings us back to our original question. What color is a black hole then? Scientists recently took the very first picture of a real black hole, and you'll notice that it doesn't look very black. The reason is because around the edge of the black hole there's a lot of matter that's spinning in towards the black hole, and it heats up really hot and it lets off a lot of light because it's so hot. So I don't want to talk about that color of the black hole. I want to talk about the actual black hole within the event horizon. So the center here, what color is that actually? Well, we know that anything that enters within the black hole's event horizon can never escape it, not even light. So you may be tempted to say that a black hole is the truest black that there actually is. But that's not really the case. The reason is because of something called Hawking radiation. At the edge of the event horizon of a black hole, there are quantum fluctuations that happen. And right at the edge, a photon and an antiphoton can appear at the same time and then annihilate each other. But if they happen to fall right on the edge and one of them enters the black hole, that means the other one can exit the black hole. And so black holes can actually emit small amounts of photons. And the Hawking radiation can be equivalent to just assigning a temperature to a black hole, a black body radiation temperature. Now, surprisingly enough, the larger the black hole is, the smaller that temperature is. For example, the supermassive black holes that have a mass millions of times more than our sun have a temperature of just around 1.4 times 10 to the negative 14 Kelvin. So pretty much the coldest thing that could possibly occur in the universe are these supermassive black holes. So these supermassive black holes are not letting off a lot of Hawking radiation. You're never going to be able to detect any photons coming off of them because of that. But surprisingly enough, the bigger the black hole is, the less Hawking radiation it emits per area. So that means that the smaller black holes actually appear hotter than bigger ones. For example, if our sun turned into a black hole, then it would have a temperature of 0.000000006 Kelvin. So that's warmer than a supermassive black hole, but still extremely cold. Given that the cosmic background radiation temperature is around 2.7 Kelvin, that means that you could never detect the radiation coming off even a solar mass black hole. But it may be possible that there are actually smaller black holes than this. For example, if the asteroid Ceres were able to become a black hole, it would be small enough that it would emit enough Hawking radiation that it would be about 122 Kelvin in temperature. Now that's still really cold, but we're getting closer. What if we took something even smaller than that? Let's say something that had around the diameter of 330 miles. If we took that and condensed it down to a black hole, then it would actually have a temperature of 1200 Kelvin. Now what does something look like when it's around 1000 degrees? It looks like this. You'll notice that as I heat it up, it starts to glow this bright red color. So what you're seeing here is what a black hole would look like if it had the size of a protoplanet or some small planet. Now the Schwarzschild radius, which means where the event horizon would actually be a bit smaller than this, probably about this big. And if you had an even smaller black hole, it would emit even more radiation. In fact, they can start to emit so much radiation that they don't just appear a faint red or anything, but they actually start to appear bright white, like a sun. So it turns out that super tiny black holes aren't actually black anymore, but they can actually appear red and even bright white, and even further than that, start producing even X-rays and gamma rays. Now once a black hole is this small, it's extremely unstable because it's glowing so much, so it's actually evaporating a little bit. It's releasing some of the mass that's inside of it as energy, as light. And so the smaller they get, the more energy they release, and so they eventually create this explosion because they reduce in size so fast that they just lit off this puff of light. Now scientists have been looking for these bright blasts of light that come from micro black holes evaporating, but they've never been able to find one yet, so we don't actually know if micro black holes exist. This horizon black mass was previously known as singularity, but they changed the name and made it even darker. And previously it was really hard to get a sample of this, but they're actually going to start selling it to the public. And thanks for watching another episode of the Action Lab. I hope you enjoyed it.